Hello, my name is James and this video is going to be on the topic endurance training with low carbohydrate availability. Now I know you're probably thinking this unusual training method goes against everything you've been told before, but the aim of today's video is to show you why training with low carbs is being considered as a good idea for endurance athletes. I'm also going to show you some studies that have applied several different practical strategies to do this, and I'll go through these strategies one at a time. We're also going to see if any of these studies evidence improved endurance performance as a result of training with low carbohydrate. So before I summarise the findings at the end of the video. So without further ado, let's take a look at the method behind the madness and see what effect carbohydrate has on physiological adaptations to endurance exercise. When we do endurance training, we get a build-up of metabolites in the muscle, which activate the protein kinases AMPK and MAPK, the former being a major metabolic activator in the human body. These kinases then signal to PGC1 alpha, which through the activation of transcriptional factors induces the following adaptations associated with endurance training: angiogenesis, increased mitochondrial density, specifically increasing enzyme activity. During exercise, more energy is derived from fats. And finally, increased expression of slow-twitch muscle fibers. Carbohydrate prevents AMPK phosphorylation, which means these downstream events and ultimately endurance training adaptations are restricted. A further endurance training adaptation is a higher rate of oxygen consumption. Many of the studies I use today used indirect calorimetry to measure fat utilization by looking at respiratory exchange ratio, or RER, which is measured in the following way. Endurance athletes tend to exhibit the following when tested. The lower the RER is, the more fat is burned for energy. Taking all these things into consideration, it may be beneficial to train without carbs. One way to do this is to train twice a day. This works by depleting glycogen in the muscle in the first session, and then without replenishing it by eating, train again a short time later. This has been tested several times with interesting results in both participant physiology and performance. In a study conducted by Hansen et al., participants took part in 10 weeks of seated knee extensor exercise. In this clever within-subject design, participants trained one leg once a day for 5 consecutive days and the other twice a day, every second day, as a method of training with depleted muscle glycogen. Differences in endurance performance between the two legs were measured with a time till exhaustion trial at 90% of a pre-recorded watt max on the knee extensor apparatus. The results were pretty astounding, as the increase in time to exhaustion was 40% greater in the low leg than the high, and this is reflected in the resting physiological changes that show citrate synthase activity was twice as high and that muscle glycogen was also increased beyond the high leg. Although the study shows that there may be some merit in training with depleted muscle glycogen, there are some noticeable criticisms of the study design. Let's now take a look at a study conducted by Yeo et al. That addresses these issues and see if the results are similar. Yeo et al. Used a cycling protocol more reminiscent of endurance training. This between-subjects design saw one group train once a day, whilst another trained twice every second day for 3 weeks, where training sessions alternated between steady-state riding and interval training. Although it was impossible to make the study blind, unlike Hansen et al., effort was controlled by offering monetary incentives for the best score in the interval training. Despite this, it was noted that the low group performed considerably worse. A 1-hour time trial performance was performed to see differences in performance, and this was preceded by a steady-state cycle to look at metabolic changes. In contrast to the Hansen study, no performance benefits were shown as a result of training with low glycogen levels, and this despite a number of enhanced physiological adaptations that should in theory improve endurance performance. Study design may have been a key factor in these differing results, particularly when it comes to the length of the training protocols. This is proved because although originally intensity was significantly lower in the low group during interval training for the Yeo study, in the 3rd week they were much closer to the high group in terms of power output, and had the training gone on for several more weeks, differences might have been observed in performance, like in the Hansen study. Future research must take this into consideration. In addition, training like this may cause overtraining syndrome, potentially leading to injuries. As well as this, the last studies mentioned were not carried out on highly trained athletes, who are the people we should be tailoring this research for, as it is they who need these fine performance advantages. Also, the protocols were short to medium in terms of length. Therefore, for the next strategy of training with low carbohydrate, I've carefully selected 2 studies that examine the effects of a high-fat or ketogenic diet on elite athletes and the effects on different length performance tests. Let's first take a look through at how a ketogenic diet works though. In theory, when we consume vast quantities of fats and restrict carbohydrate, we become more reliant on fats as an energy source. This is demonstrated on the right with these graphs of substrate utilization in keto-adapted athletes. As muscle glycogen is severely limited in the human body and fat is vastly more available, it has been theorized that using more fats and sparing carbohydrate at higher exercise intensities may be beneficial for exercise performance. In a crossover design, Rowlands and Hopkins assessed the effects of the following 2-week diets on performance in nationally competitive athletes. The cycling protocol used to assess the effects of each diet was 5 hours long and included 2 tests, one to test short endurance and another to look at the effects on ultra endurance. Submaximal tests were carried out in between to look at the utilization of fats for energy. Results showed no difference in performance time in either time trial, despite a trend towards higher power outputs after the carbohydrate diet in the short endurance test and fat diets in the ultra endurance test. This was despite RER being markedly lower in the submaximal tests after a high fat diet. These results could have been due to the design of the study, however, and could be the result of the following problems. These are criticisms Vogt et al. Aimed to address in a different study a year later. Vogt et al. Placed their participants on 2 different diets for a longer period of 5 weeks at a time. Like Rowlands and Hopkins, they conducted 1 test of shorter endurance and 1 of greater endurance. However, they were separated by a 2-day rest to address the problem with the other study, and they found very similar results, with no difference observed in either performance test, despite similar physiological adaptations to utilize more fat observed after consumption of a ketogenic diet. So despite enhanced physiological adaptations, this method of training on low carbohydrate yet again fails to recognize any performance benefits. However, both these studies only looked at a fat metabolism as a potential adaptation, meaning neither considered any other changes that may have affected results. Furthermore, a ketogenic diet is notoriously unpalatable. I could see you eating a bowl of cream cheese for your breakfast. And if there's no definite benefit to performance, why go through that torment? There is one more strategy of training on low carbohydrate availability, which is more practical, and that is training fasted before breakfast. In a between subjects design, Van Proyen et al. Aimed to see the effects of 6 weeks of cycling in the fasted state on performance. Before and after the 6 weeks, 2 trials were conducted, a submaximal 2-hour test and a 1-hour time trial. Results revealed the fasted group showed several metabolic adaptations that were heightened beyond the fed group, but again, no performance benefit had been shown. The reason may be due to genetic differences which comes with the between subjects design and the small number of participants. Conversely, in one of the only studies to look at women, it was found that VO2 max was increased in the fasted group over the fed group after 5 weeks of ET. Interestingly, there were some gender differences in metabolic activity, which seems to suggest that there may be some gender disparities in the response to training on low carbohydrate. These studies provide food for thought that certain individuals may respond better to different levels of carbohydrate and that there may not be a one-size-fits-all method to carbohydrate intake. In summary, we have explored different practical strategies that let you train without carbs, with some interesting results. although no one has contrasted different approaches before, which may be interesting in future research. The overarching theme of the present literature, though, is that training without carbs may enhance endurance training characteristics physiologically. However, we cannot recommend endurance athletes train like this, as there is little conclusive evidence that it benefits performance. Therefore, the jury is still out on endurance training without carbs.